Welcome to my talk. This is Runqing Yang from Zhejiang University. This is joint work by Rogers University, Arizona State University, Purdue University, and Northwestern University. Today, many security incidents originate from GUI applications. A typical example is spear phishing, the number one infection vector in the world, which is also popular in the APT attacks. Usually, attackers send phishing emails, message to users through GUI application and trick them downloading and executing malicious binary. Then the computer is compromised. When the malicious behavior is detected, causality analysis is an important technique for efficient attack investigation to figure out the root cause of the attack. Usually, causality analysis tracks the lineage of system objects and subjects by system events and then analyze the causal relationship to build a dependency graph. We can perform backward tracking from the graph from the alert point to find the root cause of the attack. However, typical GUI applications cause substantial accuracy degradation of causality analysis because GUI application may run for a long time and process many independent tasks, which make the graph big and complex. Here is an example of phishing email attack. An office clerk Bob received an email informing that he has been selected as a winner of an iPad and asked him to click the link to get the iPad. However, the email actually was a phishing email which led to the malicious website. The malicious website launched a click hijacking attack by creating a transparent frame on top of the get iPad button. The frame actually was a bank transfer button. When Bob clicked the get iPad button, which actually triggered the bank transfer. Fortunately, the abnormal transfer was detected, and security analysts started performing attack investigation to figure out how it happened. Typical causality analysis has the dependency explosion problem. The problem is caused by the basic assumption that within the same process, output system events are dependent on all preceding input system events, which lead to a lot of false dependency. Some approaches try to solve the problem by instrumentation to identify unit boundary and inter-unit communication. With such information, a process can be divided into semantic independent units like different web pages. Only system events within the same unit have causal relationship, which solve the dependency explosion problem. However, instrumentation is not practical. Furthermore, even all attack-related events are accurately founded, like the left picture. It is still hard to recover what happened from the user perspective. The question is Bob an insider attack or who stole the money or just a victim of social engineering? Without knowing more contextual information, it is impossible to answer such kind of questions. The above three limitations motivate the following design goal for our system. First, accurate. It should produce accurate investigation result by mitigating dependency explosion problem. Second, applicable. It requires no actual system change like instrumentation and cause low overhead so that it can be deployable in the enterprise environment. Third, visible. The output should be visible to human investigator so that they can easily understand what happened with the application contact information. Then we build our system UIScope. The key idea is combining low-level system event log with high-level user interface UI logs. Low-level system log can fully recover what happened in the system. High-level UI logs first can provide better visibility from the user perspective, and can also be used to split system events into units to mitigate dependency explosion problem. More important, both logs can be obtained without instrumentation. Comparing to existing approach that attribute system events to a whole process, UIScope attributes system events to UI elements. Here is an example. The upper part is the GUI panel user can see, and the lower is the UIScope dependency graph. The hexagons in the graph represent the UI element. For example, the node edge represents the transfer button. From the graph, we can see the abnormal transfer was caused by the transfer button. And in the same web page, there is another clickable button called Get iPad in the same identical position of the transfer button, which means that this is a click hijacking attack. Furthermore, we can trace back to the link on the Gmail web page, which implies this is social engineering work. UIScope have two major components. Event collector collect UI logs and system logs independently. Then, event analyzer first perform causality analysis on system log, UI logs and system log independently, and then attribute system events to UI elements to output a correlated graph. To monitor UI logs, we build an instrumentation-free collector based on accessibility library. Accessibility library are original designed to help disabled people control electronic devices. It provides UIScope two capability. First, get notification of an UI event like a button was clicked. Second, retrieve information about UI elements like the title of a window. The collected UI logs are sent to UI Event Analyzer, whose goal is to build dependency between UI elements. However, as far as we know, no existing work built dependency graph based on UI logs. Thus, we need to define a lot of dependency for UI logs. First, UI content dependency. UI elements are organized in a tree structure. A parent tree node represents a larger element such as a web page, and all the child nodes represent sub-elements in the web page. Such affiliation of parent and child UI elements are defined as UI content dependency. When a UI element change directly affects other UI elements, we say they have UI control dependency. There are two types of control dependency: add element and remove element dependency for adding and removing UI elements respectively. Here is an example. The upper is the GUI panel and lower is the UI dependency graph. When the link was clicked, the Gmail web page is removed, and then the malicious web page are added. Thus, we will first create a remove element dependency pointing from the link to the Gmail web page, and then create an add element dependency pointing from the link to the malicious web page. To monitor system events, we build an instrumentation collector based on built-in audit system, event tracing for Windows. ETW has been adopted widely for its low overhead. Then system event log are sent to system event analyzer, whose goal is to build dependency between system object and subject. Here we follow the standard dependency generation method used in previous paper. Here is the typical example for the attack. After building dependencies for UI logs and system logs independently, we attribute system events to individual UI elements instead of a whole process to mitigate the dependency graph, dependency explosion problem, and provide better visibility. However, UI logs and system logs are captured from different layers. How to correlate them is a challenge. We make two observations. First, system events and UI events are typically triggered by the same user behavior at the same time. That means two categories of events are mostly time-aligned. Second, some system events like socket read to download a file in the background may not be in the same time window of the corresponding UI event like the download button click. However, its initialization, like the socket creation, can be correctly time-aligned with the UI event in most of the time. Based on two observation, we build two approach. First, timestamp-based correlation. System events occurring between two UI events chronologically would be attributed to the former one. Second, initial event-based correlation. For system event related to a system object, we will first trace back to the time when the system object was initialized and then perform timestamp-based correlation again. With such correlation techniques, we can merge the two graphs and get the final dependency graph we mentioned before. To evaluate the runtime overhead, we select 14 applications from different categories. The results show that UI collector runtime overhead is less than 1%, which is reasonable because UI events are relatively small. Then we evaluate how accuracy UIScope attributes system events to UI elements. We first classify GUI application into two categories, static and dynamic, based on whether there are many activities triggered in the background without user interaction. Notepad, PDF readers are typical static applications. The results show that UIScope works well for static applications over 99% accuracy. Which is also reasonable because for static applications, UI events and system events are typically triggered synchronously. For dynamic application, we evaluate UIScope on Chrome, one of the most complex dynamic applications. When only timestamp-based correlation enabled, it can correctly attribute most of events. When with initial event-based correlation enabled, it can further increase the true positive and decrease the false positive, which confirms to the two observation we mentioned before. However, it still has some false positive because some website created a newly socket in the background. However, the number of unique domain or false positive is relatively small. We can see most of them are related to advertisement, Google servers, or social media. UIScope does suffer some limitations. First, if initialization of system events and UI events do not appear close together in time, our system could result in wrong correlation. Second, our system only works on GUI applications. To summary, we are the first to provide accurate and high visibility attack investigation for GUI applications without instrumentation. The core is to leverage user space UI logs to complement kernel level system events with more contextual semantics and provide divide system events into units to mitigate dependency explosion problem. The evaluation showed our system is lightweight and efficient. Thanks for listening to my talk. I'm happy to answer any questions now.